Now that we know a little something about imaginary numbers, let's take a look at solving a quadratic that would be previously unsolvable for us. So we're going to allow or work in the complex number system. Which allows for both real and imaginary numbers. Okay, so if you wanted to factor this, you'd be looking for numbers that add to 2, multiply to 5. Probably not going to find them quickly, so we go to the quadratic formula. Negative b plus or minus the square root of b squared, that'll be 4, minus 4 times a times c. So 4 times 1 times 5, all over 2a. Okay, and that gives us this. And at a certain point here, we probably, if we were working in the real number system, we'd just say no solution. If we allow for complex numbers, then let's keep going with this. Negative 2 plus or minus the square root of, okay, square root of negative 16 is the same as square root of 16 times square root of negative 1, or 4i, all over 2. And we reduce that, and that would be negative 1 plus or minus 2i. So you've gotten numbers at this point that are going to allow you to factor, but they have this complex component in them. Now you might not believe me that these numbers actually work. So if we had gotten x's, say 2 and 3 as our answers, then we'd know that it factors to x minus 2, x minus 3. We got these complex roots, so let's see if the factored version really works out. So in the end, we should have x minus negative 1 plus 2i and x minus negative 1 minus 2i. Okay, let's clean those up a little bit. That would be x plus 1 minus 2i, x plus 1 plus 2i. And we want to check to see if that actually expands out and gives us x squared plus 2x. Okay, let's go through the process. So we'd have x times x. That gives us x squared. X times 1 plus x. X times 2i gives us 2ix. Then we'll have 1 times x, so plus an x. 1 times 1 plus 1. 1 times 2i plus 2i. Next one's going to be minus 2ix, minus 2i, and finally minus 4 rather, I squared. These last two terms. Okay, collect our like terms. We have an x squared, we have two x's. Let's see. Oops. 2ix and negative 2ix, those are gone. 2i and negative 2i, those are gone. That just leaves us with plus 1 minus 4i squared, which we know is negative 1. Oh my gosh, it really works out. So these complex roots really do allow us to factor these. There's some practice on Math Power 11. That's what the MP11 stands for. Page 186, numbers 56 to 87. Now, a lot of people think, all right, well, that means we must have found something out about the graph of y equals x squared plus 2x plus 5. We know that it opens upwards. But if we had used discriminant, which is just the b squared minus 4ac part of the quadratic formula, we would have said it's negative and there are no x-intercepts. Nothing has changed in that respect. We still know that this opens up and it has no real x-intercepts. So these are not telling us the coordinates of something in the xy plane where x and y are real numbers. So the short answer to the question, what new insight have we gained into the graph of y equals x squared plus 2x plus 5 by allowing for complex numbers, is not much. If we're still going to graph on the x and y axes, then we don't know any coordinates of x-intercepts because they don't exist. Okay, I don't want to get into a whole big thing on what complex numbers are good for. You can Google that. There are some great explanations. There are some terrible explanations. But I just want to get you thinking about one of the possible applications of this and something that might have bothered you before. So contrary to Cardano's beliefs, imaginary complex numbers do have applications in many areas: electrical engineering, vector-style drawings, they're easy to rotate, roots and fractals. And I think most importantly, they just allow us to expand our concept of numbers. So when you have this equation, x squared equals 1, you know that there are two solutions. There's x equals 1 and x equals negative 1. But when you have x to the third, we've typically said there's only one solution to that. It's the number 1. And it always kind of bothered me that this one would have more solutions than this one. If we allow for the complex number system, it turns out that we get more solutions. So we get 3 solutions for x cubed equals 1. Now, still only one of them happens to be a real number and probably useful to us in a lot of context. But there are 2 other numbers that are going to work in that equation, that if you put them in and you cube them, they're going to give you positive 1. Let's try that for maybe one of those 2 solutions. Okay, so if I took negative a half times root 3 over 2I and I cubed it, that would be equivalent to multiplying it by itself, then multiplying it by itself again. Okay. We may run out of space here. So I'm just going to take the last 2 and FOIL them or use the distributive property. That's going to give me a quarter. Minus root 3 over 2I, or root 3 over 4I, rather. Okay. The next one's going to give us another minus root 3 over 4I. And then the last one's going to give us positive 3/4 I squared. Okay. That's just what's coming from these 2 brackets over here. Now, if we want to cube that, that means we have to, first of all, clean it up. So if I go further with this, this will be a quarter minus root 3 over 2I minus 3/4, because that's 3/4 times an I squared, which is minus 1. Okay, which in turn is negative a half minus root 3 over 2I. So that's what happens from the last 2 brackets. Let's go back now, and here's the first bracket, root 3 over 2I. Okay, here's the last 2 brackets worked out. Negative a half minus root 3 over 2I. Ooh, look at that. They're binomial conjugates now. That would mean we'd get 1/4 plus root 3 over 4I minus root 3 over 4I minus 3 over 4I squared. Oh my gosh, look at this. These ones are going to add to 0. We'll have a quarter plus 3/4, which gives us, yay, let's do it in something fun, equals 1. Okay, so this section over here ends up giving us 1. So there is another root to x cubed equals 1. It just happens to be a complex root. There are more solutions than there initially seem in the real number system. What's it good for? That's something that you can really investigate on your own, depending on what level you want to get into this. Now, a lot of people say, well, what's this good for? I've given you a few examples up top. I want to also make the argument that we accept a lot of things that it's not always clear immediately what they're good for. So it can be difficult to wrap our heads around the notion of complex numbers. But we accept some really abstract concepts already. That, first of all, that numbers are things, even if they're not counting, measuring, or ranking some physical object. So when you learn to count, you were counting actual things. You might have been counting coins, you were counting whatever you had in your counting books. But right now, you think of 3, and you know what 3 means. You don't have to think that it's 3 pencils or that it's 3 ships. So we accept that numbers are things, even when they're not physical. We accept that irrational and negative numbers exist, even if it's very difficult or impossible to use them for measurement, and some would say, and therefore in the real world. So the fact that I showed that in this triangle, this is root 2, it's still hard to build a ruler that says root 2 on it, root 2 centimeters. We accept that 1 and negative 1 represent the same quantity, but just in opposite directions, so above 0 and below 0. We accept, this is a wild one, that 2 negatives multiply to make a positive. I mean, why would we define that? I think one of the reasons is that this 5 times 2, you know that's 10. It needs to be equivalent to, say, 6 minus 1 times 3 minus 1. If we want our distributive property to work, then we know this should give us 18. Okay, this should give us negative 6. We're probably okay with a negative times a positive makes a negative. So the only way that this whole thing can work out, and for us to get 10 like we should, is if the negative 1 times the negative 1 give us a positive 1 and 10. But it's still pretty hard to justify. And yet, we accept it. And that's to allow the other laws of mathematics to stick together and actually work. That mathematics seems to be able to describe a lot of what happens in nature despite the fact that much of it wasn't necessarily developed, invented, discovered, TOK debate for that purpose. And just to give you a little sort of teaser here, we found 3 solutions to x cubed equals 1. Guess what? In the complex number system, you'll be able to find 4 solutions to x to the 4th equals 1. You know 2 of them already. They're the numbers 1 and negative 1. But you're also going to have solutions of I and negative I. Negative I. You can try it in there. If I put in I to the 4th, we already defined that equals 1. If I put in negative I to the 4th, negative number raised to an even power gives us a positive, so we just get I to the 4th. That really is 1. And we'd have 8 solutions to x to the 8 equals 1. And they occur on our complex number plane. Right here's 1. Here's I. Here's negative 1. And here's negative I. They're evenly spaced out rotationally on the complex number plane. Pretty creepy. All right, so if you're interested in going further with this, you might be interested in de Moivre's theorem. But that's about where we're going to stop it. And really, all I wanted to do with complex numbers is introduce you to the idea that there is this number system that involves the square root of negative 1, and that a lot of the rules work exactly the same way. So in the last section, we looked at rationalizing denominators. We looked at not wanting i's on the bottom. We looked at the fact that you could use it in quadratic formula and come up with these complex solutions, but that wouldn't necessarily help you to graph it in the xy plane.